Hi, I'm Lon Schleining. I live and work in Southern California. I work with curves a lot. 3 ways to make a curve, really. Cut it out of a solid block. This part is cut out of the solid block also. Use bent lamination, that's thin strips glued together around a form. That's how this is made. Or bending with heat, steam usually. That's how these parts are made on this old office chair. It's no accident, incidentally, that this office chair is all oak and this continuous armchair from Thomas Mosher is cherry. Stick with this. In the course of the DVD, you'll learn why that might be a good selection and a lot more. Come on into the shop. Let's bend some wood. In the video, we'll concentrate on steam bending and bent lamination, getting a feel for both to make that decision between them easier. Once you become more familiar with these techniques, you'll develop your own methods for making them work on your particular situation. A bent lamination is thin strips of wood glued, bent, and clamped together around a form. When the glue cures, it keeps that shape. You can see the layers and how well the grain matches on the end of this chair arm. The arm on this Thomas Mosher continuous arm chair is an example of bent lamination at its finest. This is as good as it gets. Building the form is a logical place to start, assuming you have the part drawn full size. Here's the part right here. I draw the part full size, then draw the form on which the part gets bent. I draw the clamp blocks and figure out how the clamping sequence is going to go. I make sure my clamps will work for the form I've drawn. All this is part of my preparation for actually bending the wood. Plywood and MDF are the most common materials for forms. Plywood lasts longer, but MDF is more uniform and easier to work with. Here's the part. I spend as much time as it takes to smooth the jigsaw cut with hand tools or sanders. A little of this goes a long way. My old belt sander held in this jig doubles as an edge sander. Once you make the first layer smooth, it's a simple matter to duplicate the shape with a router using a flush trim bit, using the first layer as a template. Then stack the layers, glue and screw them together, and you're nearly finished with the form. A two-part form consists of a solid male convex form and a solid female concave form. You can see that as clamp pressure is applied, the forms apply pressure in only 3 or 4 spots along a bundle of laminates. A much more workable approach to the two-part form is to simply cut the concave portion into individually movable segments and use them as clamp blocks. I drill holes in the male part of the form using a large drill bit in the drill press. This positions the clamps and speeds the process of clamping up the part. I build guide blocks into the form so I can edge clamp the bundle. This keeps the part lined up on the jig properly for clamping purposes. I use the blocks themselves to set the angles on these edge clamp blocks so that it's pretty much in the center between each block. Cellophane packing tape is a great way to keep glue off of the form. I virtually cover the entire form with it. Make sure there's a way to hold the form to the bench. When you're in a hurry to clamp the part, you won't want the form sliding around. If the radius is greater than about 12 inches, I use this router guide to make the first layer of the form for a pattern. A shank-mounted bearing flush cuts the MDF even with the guide batten. It's a setup I've used countless times to cut curves, especially if the curves aren't true circles. It's quick and easy to make a pattern using the battens. I run these battens through the planer to mill them to size. I have to make them small enough to bend around whatever radius I'm using. Once I do, it's very simple to nail them in place with a pin gun. I use 2 battens to stabilize the router. If I had only 1, the router would rock back and forth. With 2, it's very stable for the length of the cut. Jigsaw close to the line. The batten setup works great to make the pattern. The pattern works great to make the form layers. I use the pattern to mark the layers, then jigsaw close to the line. I fasten the pattern to the individual layer, then use the pattern to guide the flush trim bit. So with this pattern piece, we can make as many duplicates as we want using the same router setup, using this as a pattern. An individual piece should be easy to bend around your form using only light finger pressure. I usually cut a sample piece at some arbitrary thickness and give it a try. If it's too stiff, I plane it down a little with the portable surface planer. If it's still too stiff, I plane it down some more. Eventually, it's thin enough to bend around the form very easily. That's how I determine the thickness of the laminates I need for my project. Once you figure out how thick each piece is, it's pretty simple to find out how many you need. What I do is mill a length of the material the right thickness, then chop it into short pieces. I stack them up until I get the right height. That's how many I need. If you like, you can figure it out mathematically, but it's a good idea to check using this method anyway. So what's the best way to cut thin strips? I prefer the table saw because I think it yields the most strips on a given board and it's very fast. There's a very common table saw gizmo for ripping strips as off-fall on the table saw. It's fast, easy to make, and using this concept makes the operation a lot safer than cutting thin strips between the blade and the fence. This little device is held in the slot. This screw goes in and out, and so I can set this to cut off the same amount every time. Just move it back this way, tighten it down. Then I move the fence in until the board contacts this just right. Now I can make the cut. And as you can see, the cut, we're going to use the off-fall piece that's just that same thickness. But there is also a very nice store-bought model available from Rockler. In my shop, I do not normally joint boards prior to gluing. My usual procedure is to go right from the table saw to the glue table. That's why it's natural for me to use this same technique when milling bending laminates. I get a nice cut on the table saw, perfect for gluing. The main limitation is that the strips cannot be wider than about 2 inches, the maximum cutting height for most table saws. If you need wider strips, you might be able to make 2 cuts, one from the top and one from the bottom of the board. Even cutting from two sides is limited to about 4 inches. But as you see, the cuts don't line up well enough to glue as is. The piece will need to go through the planer anyway. There are dozens of different tabletop planers, some better than others of course, but all offering very precise cuts. The setup I use couldn't be more simple. I have a piece of 3/4 inch melamine with a small cleat at one end to raise and lengthen the feed table. I lube it up with top coat, run the pieces through the planer in the normal fashion, and that's all there is to it. I take very light cuts and feed the laminates in nose to tail. Once in a while the planer will chew up an especially thin piece or one with a flaw, but not very often. Many people like to use the bandsaw for ripping strips, thinking the narrower saw curve of the bandsaw will produce more bending strips than ripping them on the table saw. By the time you joint and/or plane both sides of the laminate you've cut with the bandsaw, you've removed just about the same thickness as the table saw curve, maybe more. Even the best planers have a little bit of snipe, so the ends, the first 2 or 3 inches on each end of the board, have to be discarded. I started with 2 6-inch wide boards. I cut 1/8 inch strips out of each of them using the bandsaw for one and the table saw for the other. The yield was 25 laminates using the table saw and 29 using the bandsaw. But keep in mind the bandsaw laminates lost about 4 inches of length as they went through the planer. As with all working techniques I can think of, use the one that best fits your equipment, experience, and comfort level. You can also use veneers. Using sliced veneers is a great option, especially when the radius is tight, requiring very thin laminates. They're available at 1/8, 1/10, and 1/16 inch thickness from a variety of sources. Since the veneers are sliced with a knife and not sawn, there is virtually no waste, and the grain match is nearly perfect. Whenever I decide to use veneers this thin, I make sure I have a very solid and uniform clamping form like the segmented 2-part form we made earlier. The clamp blocks have to be nearly continuous. Otherwise the bundle will be thinner where the clamps are and thicker in between, creating a porpoising effect. This spreads out the clamp pressure and makes the finished product look even without dents from concentrated clamp pressure. Now I'm going to do a dry clamp. I've been at this a long time. I have glued up hundreds of bent laminations. The reason I dry clamp is to get familiar with the process. I get all the clamps where I need them. I get all my clamp blocks where I need them. I make sure everything is the right size. It's a really good thing if the clamps are long enough for the form I've built. It's a really good thing if I have enough of them. I want to find all that out before I mix the glue. In this case, I'm starting in the middle, but sometimes I start at one end. In either case, I clamp progressively toward the end or ends once I start applying clamps. Now's the time to apply 1 or 2 of what I call edge clamps. The bend, if left to its own devices, will bend around at an angle to the form. It's rising on the left and lowering on the right. By applying pressure in this direction, the laminates are forced into position so they line up with their neighbors. We want to encourage the plies to slide on one another in what amounts to an east-west direction. But we need to carefully control them north and south to keep the bundle intact. I always clamp it up dry. I invariably discover something I wish I had known in the process, like this. This block is jammed in here. The darn block is too wide. I don't want that block. It's really jammed in there. I don't want that block to interfere with the clamping pressure. So what I have to do is take this block and make it narrower. If I had not discovered that, I would have to go narrow those blocks with glue dripping everywhere. So I have all the clamps in place. I know it's going to work like I want it to. Now's the time where I'll take everything apart again and I'll spread glue. Then I can bend for real. Woodworkers often learn what glue not to use the hard way. The good news is the most suitable glues are readily available and also have a pretty long working time, which will help with gluing and clamping. Most of the time I use this Weldwood plastic resin glue. I've used enough of it over the years to have developed a good working knowledge of its quirks. Yes, I do read the label. Amazing how much useful information is right there in the fine print. Clamp pressure, working time, working and curing temperature ranges, all kinds of useful stuff. Cover the bench with plastic or paper first, and I tape it down so it stays put. First we'll need an electric mixer, some pantyhose, a mixing bowl or two, disposable foam paint rollers, and make sure you have a good supply of disposable gloves and a dust mask. This is my mixing arsenal. When I mix glue, my setup keeps the mess to a minimum. I dole out enough powder to mix about twice the amount of glue I think I'll need that day, knowing full well I'll be throwing away what I don't use. I pour in a large amount of water initially, stirring it in at first just with the beaters, without turning the mixer on. Once the water is mostly mixed in, I fire up the mixer, adding water a little at a time. The glue should be pretty thick at this point. If it's thicker than peanut butter, add water as needed. The label says add water until you reach the consistency of heavy cream. It's pretty easy to add too much water toward the end. If you do, just add a little bit more powder and mix well. It's lumpy, right? But not to worry, just go to the next step. You'll need an extra bowl or coffee can for this step. I cut a 12-inch length of pantyhose. Stretch the strainer over the rim of the bowl and pour the mixture into the strainer. It's just like milking a cow. You squeeze the mixture through the strainer, leaving all the nasty lumps inside the pantyhose sock and the smooth, lump-free mixture in the bowl. So how in the world can I spread glue fast enough? Spreading the glue quickly enough is not just a matter of hurrying. There's a system anyone can use to speed the process, and you don't really have to hurry. I've already dry clamped, and now I clean the dust off of every square inch of glue surface. Sometimes I use a vacuum, sometimes I use compressed air. Remember, we were careful to get a good grain match. Now we have to make sure we don't shuffle the laminates during the glue up. A triangle mark across the bundle makes it easy to keep track of the sequence, which is top and bottom, and if any of the laminates is switched end for end. I line up the laminates edge to edge. I'm careful to place the two outside pieces face down on the plastic. This sets up the entire bundle to coat one side with glue. Forget about using a brush. You simply don't have the time. I either use a notched trowel or a paint roller to spread glue, and a paint roller is probably faster. Then I start spreading glue like mad. If I'm rolling, I roll enough glue onto the surface that it doesn't make noise. Keep dipping and rolling until the rolling action gets quiet. You can hear that sound. We're going to add a little bit more glue, and that sound goes away. That way we know we have enough. Once I've covered one side of the pieces, I flip them. I'm careful to place the first two pieces glue side to glue side on top of one another, moving the laminates together again so the edges touch. I repeat the process on these surfaces until I have the whole dripping bundle of glued strips coated. Once I've covered the pieces, I stack the laminates on top of one another until I have a whole dripping bundle of strips. This is where we need to monitor the location of the triangle mark. Check the mark one more time to make sure. Okay. One last step I use is to keep the bundle together using stranded packing tape at intervals along the bundle. The tape makes it a lot easier to handle the bundle during the clamping process. More importantly, it reduces open time. This is the very limited time glue has before it skins over if left exposed to the air. See how fast that was? We coated the whole batch in nothing flat, giving ourselves plenty of time to clamp. Just be sure to remember we're not being graded on neatness, only speed. It's tricky and messy getting started. It helps to have a center line as a point to line up. I can't overemphasize how important it is to apply clamps progressively out toward the end of the bend. It doesn't matter whether we start at one end and work toward the other end, or start in the middle and work our way outward both directions from the middle. In either case, we gradually squeeze the glue out toward the ends of the bundle, not force it in toward the middle of the bend. Once I start applying clamp pressure, the pieces grab right away. So I'm careful to confirm that the whole bundle is on the form like I want it before I get too carried away clamping. I try to back away at this critical point to see if I notice something going awry I might not have noticed otherwise. It looks like it should. Nicely lined up on the form, edge clamped, and ready to be bent and clamped the rest of the way. I prefer bar clamps like these. They're very fast to apply and provide positive clamp pressure adjustment. As you can see, they can be easily adjusted with one hand. I get the clamps as tight as they're going to be as I go. When I have all the clamps in place, I can't resist checking them all to make sure they're tight, but I try not to adjust them too much. The last thing I do after the clamps are in place, if I remember, is take a stick or my gloved finger and scoop off as much excess glue as I can. The glue is a lot easier to remove now than after it's cured. When the last clamp is removed, I jar the piece just a bit to make sure it's broken loose from the form. Shards of the glue are sharp as a chisel. If I forget the gloves, I at least try to remember the Band-Aids. Okay, we're loose from the form here. It's tight up against the form. A lot of people wonder about springback. Right there is how much total springback we have, about a hard 1/16 of an inch. Yeah, down here I put a couple of blocks just for the heck of it, and I put the tape side out, so they're really stuck to this mahogany. I can easily see if there are any gaps between laminates where I didn't get good clamp pressure. If I'm not happy with the glue up, I quickly cut the piece up and start over before I have too much time to grumble about it. The good news is the part is perfectly bent to the right shape. The bad news is it's covered with glue. Take heart. Milling away all that glue will be easier than you think. I use this little hook scraper to remove most of the glue. If I keep it really sharp, it works amazingly fast. I use a very fine metal file to sharpen it. This is a two-handed tool, so the part needs to be securely clamped to the bench. I pull with one hand, steer and apply light pressure with the other. I have to keep in mind the scraper will dull after only a couple dozen cuts. Then it's back to the file. The scraper does a truly remarkable job of removing glue, at least with smaller parts. And I finish up with the belt sander on edge. By hooking the belt sander up to a shop vac, most of the dust is sucked into the vac. It's good if you have a very fine filter in the vac. The dust from this glue can be very toxic for some people. Any trouble breathing is a 911 call. This is about how far I take the scraping and sanding. A few glue spots show through, but it's relatively smooth on both sides. Then it's off to the portable surface planer. I put the best side down on the bed of the portable planer. I feed the bend through the planer, guiding it so it doesn't get stuck. After a light pass or two on one side, I flip it over for another couple of light passes. I take no more than a quarter turn. A quarter turn on my planer equals a cut of about 20 thousandths. for each pass. I continue until the piece is down or near its finished dimension. At the rough planing stage, we have it down to where it basically looks like a solid piece of wood. That's what we're after, this look right here. Where it came beyond the form, we can see there's some spread between the layers here. But this is the meat and potatoes part. We made this extra wide because I'm really hoping to be able to get 1 5/8" out of it. And we're just about there right now with both edges nice and clean. We have 4 of these parts to make, so I'll wait to final dimension this till we get the other 3 done. But that's what we're after right there. Once the piece is cleaned on all 4 sides, you can add a detail to the piece in the router table. In this case, I'm using a roundover bit to smooth one edge. I make an initial pass with the bit retracted a little bit from where it will be for the finished cut. I extend it gradually until the cuts blend into a full round. One of my favorite quirks of nature is the notion that we cannot overheat a steam box no matter how hard we try. If I hook my largest boiler to my smallest steam box, run the burners full blast all day, the temperature inside the box will never exceed 212 degrees at sea level. That is, of course, as long as we don't allow pressure to build up in the box. What's really wonderful about this phenomenon is it just happens to be the ideal temperature for bending wood. When we steam a piece of wood, we heat it and also subject it to moisture. So is it the heat or the moisture or both that makes the piece bend? Let's look at each separately. Bending a piece of wood like this seems impossible. Almost as soon as it starts to bend, it breaks. Bending with only moisture. This piece of wood is soaked for a week in room temperature water. Let's see how well it bends. The piece will bend only slightly more after soaking than it did before. Now let's look at heat. It's common to make small bends using nothing more than a heat gun. The common thread is that they're using heat, not moisture, or at least not to the same degree, to bend wood. This electric heating blanket supplies heat and lots of it. The pad gets wood hot very quickly and maintains the heat during the bend. It's primarily used by instrument makers to bend the curved sides of their instruments. It works best on relatively thin bends. Instrument makers are not alone. Boat builders, especially in more primitive areas, to this day heat hull planks over a fire to bend them. Coopers use fire to bend barrel staves. Here we're heating pieces with steam. Over here we're heating pieces with an electrical pad, which is very hot. So it doesn't matter how we heat the piece. We heat it dry, we heat it with steam. The only important thing is the heat. The form for steam bending is similar to the one we use for bent lamination, but different in a significant way. With steam bending, spring back is inevitable. With bent lamination, it's not. The bent lamination form is designed to bend the part to the exact radius of the final shape. We design a steam bending form to dramatically overbend the part so it relaxes to the shape we really want. How much overbend is enough? This goes back to the notion of gaining a feel for the process. As close as anyone can come to an answer is to say that the more overbend, the better. It's a simple matter of making sure your bending form will overbend the piece so that when it's released from the form, the piece can relax into the shape you really want. The form has to be securely fastened to the bench. We'll be applying more pressure to the form with steam bending than with bent lamination, especially pulling the piece into shape with the handles. Steam bending forms need to accommodate very fast clamping. We need to really move quickly to get a steam piece bent before it cools. Key to bending accurately is the notion of a setting form or a cooling form. Once the bend is made on the main form, the piece needs to cool, dry, and set. The setting form will accurately hold the piece to final shape, allow air circulation, and be portable. A great way to set the bend is to place the piece of wood still on the setting form inside a drying area heated to about 150 degrees. After about 24 hours in the heat, the wood is dry and the bend is set. I typically build a new box every time I bend a different size piece. I use either exterior plywood or solid pine. I just screw the box together using exterior deck screws. It's good to remember that steel and steaming hot oak are a poor mix. If steel comes in contact with wet oak, it will make a very deep black stain. For a door, I just cut a piece that will cap the end with a couple of stops to hold it in place. It's just a friction fit. I like to build legs of some sort to keep the box elevated. I also slant the box toward the opening door so condensation runs down and out through the small cuts I make in the door. Build your steam box only as large as it needs to be and as small as possible. It's important to keep the piece off of the bottom of the box. I usually use dowels going all the way through the box for shelving. It's pretty easy to drill for the dowels before assembling the box. If you plan to bend pieces in batches, obviously the box will need to be bigger. As long as the box allows steam to circulate all around the piece inside, it's big enough. But keep in mind, the larger the box, the more steam it requires to heat it properly. Sometimes the box will heat almost hot enough, but not quite. A good alternative to acquiring another boiler is first try insulating the steam box. Rigid foam is the easiest to use because all you have to do is cut it with a knife and tape it in place around the box. Lots of people use plastic pipe for steam bending boxes. It's okay with me, but realize it tends to sag when it gets hot. Building a V shape out of lumber will support the plastic pipe and keep it from sagging. I have made and otherwise acquired lots of different boilers over the years, but these are the ones I actually use most. My large tank size boiler really generates a lot of steam or heat, easily enough to heat a box as large as I'll ever need. On the downside, it uses more fuel than my pickup truck and is very heavy to move around. But it has an open flame, and that means it's an outside-only operation. A lot of people use the popular setup for deep frying a turkey. The burner and boiler are already assembled with plenty of BTUs to heat up even the largest steam box. The biggest challenge is adapting the lid or making a new lid to funnel the steam into a hose and from there into a steam box. This steam kettle is probably my favorite. It came from Lee Valley Tools. It puts out more steam than I would have thought, boils water very quickly, and probably the safest of all my boilers since it's electric and doesn't have an open flame. The important test is to see if the box heats to the magic number 212 degrees. Here's a large box with a small kettle heating it. After 2 hours with the steamer going full blast, the temperature in the box reached a whopping 175 degrees. To raise the temperature, it's literally a matter of adding more steam. If one kettle heats the box to 150 or 170 degrees, chances are 2 kettles will get it to 212. Adding a third will only keep it at 212, not raise the box temperature even a single degree, as long as the box vents steam and does not build up any pressure. What I do is build the box first, make a wild guess as to the size of the boiler, then give it a try. If the box promptly heats to 212, great. If not, I add boiler capacity until it does. As an alternative to building a new box every time I have a different piece, this is a long box, but I'm going to be bending a piece only this long. So here's what I did. I cut a slot in the top of the box, made this partition, which effectively makes the box only this long now, just right for this piece. And I can use one kettle at a time to heat this much box. I can swap them back and forth and keep the water level full, which is going to mean I can run this all day without having to worry about water too much. We have to generate enough steam to heat the box we just made. It's obvious this kettle is being asked to heat only a pretty small steam box. The important test is to see if the box heats to the magic number 212 degrees. Holes in the box facilitate inserting a thermometer. They also allow steam to circulate. I want the box to be anything but airtight. I not only want the steam to circulate, I want to make sure there's no buildup of pressure inside the box. It's hard to find the holes sometimes. Circling them with a marker makes them more obvious, both to measure the temperature and to avoid being scalded by escaping steam. Live steam is invisible. It's only after it cools and condenses a great deal that you can see it. Most of us as kids realized that we could put our fingers through a candle flame and not get burned. We'll try that with live steam, and it's a different story entirely. If I did this with steam, without gloves on, my fingers would get scalded. Watch how quickly this candle melts. This is seriously hot. And the steam delivers the heat very effectively, making it really hazardous for humans, but great for steam bending. A drip pen under the box will save a lot of work cleaning up. Chances are we'll need to make steam for several hours. This means we'll have to replenish the water supply in the boiler. This can be a very tricky operation since the water will have to be added while the boiler is hot. This arrangement lets me add water a sip at a time. The kettle will run indefinitely as long as I don't let it run out of water. Why did this piece break? It was heated just right for the right amount of time, at the right temperature. I went slowly, I didn't hurry. So what the heck happened? For wood or anything else to start out straight and then bend into a curve, the outside or convex surface has to get longer, and or the inside or concave surface has to get shorter. Let's take the example of bending the back for a chair. Let's say we start with a board 1 inch square by 48 inches long. Then bend it around a 6-inch radius, forming a 180-degree curve. The outside surface of that board is still around 48 inches, maybe just a little bit longer. But the inside of the curve is no longer 48 inches. It has to be more like 45 inches. Where in the world did 3 inches of wood go? When we bend the chair back, we have to limit how much the piece will stretch or it'll break. When we did this, in order for the piece to bend, we had to shrink or compress the inner part of the piece. On a microscopic level, the somewhat hollow cavities in the wood that used to hold water or sap are now empty but still moist. Heating the wood slightly softens the lignin, in turn softening the walls of these cavities. Once the cavity walls are softened or plasticized, even just a little, the shape of the cavity can change, in this case collapse, allowing the cells to compress and the board to bend. Left to its own devices, the piece would much rather stretch than compress. Here's the part I want to make. A 90-degree bend, kind of thin, and a piece of oak. This form is the key to getting it all to work. This piece of steel will not allow the board to stretch. It will make it compress. As it bends, it won't be able to stretch and break. It's forced to compress. You can see that process right here on this piece of oak. It's crinkled along this inner edge so the wood is compressing. Remember, this is much longer than this. The piece of steel is bolted in here. The lag bolts go clear through the steel into the handle. It extends back this far, it's bolted in here. It comes around the back, it's bolted there. There are clamp holes so I can put clamps on quickly. Like this spot right here, I realized that one of the lag bolts right here interfered with the jig. So I just drilled a little relief hole. So the whole thing works quickly. To get enough leverage, I actually built the handle 3 times. I had it too short, then I still had it too short, and now it's finally long enough that I can bend pretty easily, but it takes a good amount of pressure. It stretches this steel, believe it or not. This blank, when I first made this jig, fit in here really tight. Now, I've bent several pieces on this. It's pushing a 1/4 inch gap here. What I do is put in Formica laminate shims to fill the gap. Then this will compress the inside, not allow the outside to stretch as I make the bend. This setup gets you going. Set up the tea kettles, hook up the parts, and we're ready to steam some wood. Heat the box and measure the temperature with a meat thermometer. Make sure it's 212. When I open the door to place the boards in the steam box, the temperature drops. I wait till it's back up to 212 before noting the time. Then it's 1 hour per inch of thickness in the steam. Wearing gloves, take out a piece and just look at it for a minute. Amazing, isn't it? After only a few seconds, it isn't even wet. I race to get to this point, the beginning of the bend. The piece cools very quickly, so there's no time to waste. But from this point on, it's go as fast as I can, but as slowly as I need to. The bend itself has to go quickly but slowly. The board needs some time to get used to the idea of bending. It's only a matter of bending and clamping gradually until the piece is on the form. I usually leave the board on the form for 5 or 10 minutes. Pop the bend out and immediately clamp the board to the setting form. The setting form will hold the shape while the bend sets. Eventually, it produces a part like this, and then I can run it through the bandsaw to get my part. Why do bends fail? Remember, if the outside stretches too much, the piece is going to break. Easily the most common and familiar bending failure. Next in frequency of bending failure comes not enough heat. This is definitely the best way to add water. You add hot water, it doesn't cool the box off at all. One of the keys to bending successfully is to heat the board evenly and thoroughly. People who are bending wood before anyone can remember realized it takes about 1 hour to thoroughly heat a board 1 inch thick. The thickness is really all that seems to matter. A board 1 inch thick by 3 inches wide will need about an hour to heat. A board twice that wide will likewise still need about an hour to heat. Flaws in the piece being bent will almost always cause a failure. This small knot will almost certainly make for an unsuccessful bend. Grain runout is where the grain of the wood does not run parallel with the board. By sighting down the length of the board, the reflection of light will indicate how much grain runout there is. The less runout, the greater the chance of a successful bend. It makes little difference how the grain is oriented in relation to the direction of the bend. There are 4 ways to tell if a bend is going to be hard to pull off. The first is the radius. As the radius gets smaller, the bend gets harder. Second is the degree of arc. A 180-degree bend is going to be harder than a 90-degree bend. Third is the thickness we're bending. As the piece gets thicker, the bend gets harder, a lot harder. Thickness in this case is measured from the circumference of the piece in toward the center point. This brings us to the 4th and possibly most important way to tell if a bend is going to be hard or perhaps impossible: the wood species. My bending motto is, you can steam bend any species you like, as long as it's oak. Now let's bend a chair back. It's a piece that's a lot longer than what we've been bending, and this time we're going to bend it 180 degrees instead of 90. The principle is the same, using a compression strap, but the setup is slightly different. These are the straps I use to make the bend for the chair back. This one has a backer block extending from the end stop out toward the bend. All you really need for the metal working is a hacksaw and some drill bits. We need some handles and back blocks. The handles extend beyond the length of the piece being bent to get more leverage on the bend. They also extend onto the bending strap itself so that the end blocks don't rotate out of position and allow the piece to pop out of the strap. It's hard to imagine how much pressure these end blocks have to withstand until you try a bend or two. We're going to make 2 different bends with this strap. No backer block. Then we're going to move this handle and we'll do another bend with the backer block. You'll be able to see why we have it. I work alone most of the time, so I tend to set up operations accordingly. On the larger bends like this one, I use a rope and pulley system. Position the center line on the center of the form. Clamp the block in place to help hold the piece until the bend is a little farther along. Keep the rope free and move it to the outside of the form to start the bend. Apply steady pressure and let the bend happen gradually. Don't force it or bend too fast. You get a feel for it pretty quickly. Turn the block around and reclamp it so that the curved side is against the bend. This bend uses end blocks, end stops, but it needs an additional backer block. The backer blocks prevent what you see here. The backer blocks will keep the end stops in line as the piece bends. With this bend, you can see that the backer blocks are doing their job. To bring the handles in the last couple of inches, I just let the clamps do the work. This bend actually took about 4 minutes from the time the blank was removed from the steam until now. That's all there is to it. Not simple, but easy to do with the correct planning. If the bend is a long one, say over 3 feet in length, the strap will need blocks to keep the strap centered on the bending piece. This is the only commercially available strap system I know of. It comes from Lee Valley. Since the strapping material itself is spring steel, it will last a lot longer than the shop-built strap. The adjustable screw mechanism means you can adjust end pressure as you bend, a very useful feature when you get into more challenging bends. It's easier to bend a square blank than a round one. Once you bend the square blank, get it bent, let it cool, then use a 1/2 inch radius roundover bit on all 4 corners. Once you sand it a little bit, it'll be perfectly round. Well, I hope you found this video useful and interesting. I think bending is a blast. Time for you to go out in the shop now, try some of this stuff for yourself. I think you're going to have just as much fun with bending as I do.